Okay, let's get started here. So this is week 13 of our class. We just have 2 more regular Tuesday classes left to go. So for today, you need to just examine subsection 3 of section 4. It's less material than normal because of the test that's on Thursday. And with this particular subsection, we're looking at regression models. Record-old regression models with a little twist to it. So our response variable is y, and it's indexed by t because we're observing y over time. We have our record-old regression parameters, our betas. We have explanatory variables, or you can call them independent variables, or you can call them covariates, and these are denoted by the z's. We have r of these potential explanatory variables. And where we normally would see like an epsilon represented as the error term, we now have an x of t. And the reason why we do that is because normally with regression models, we assume that the epsilons are all independent of one another. Here now we're going to allow for dependence amongst these error terms. And the way that we're going to allow for the dependence is to say that this error terms comes about through an ARMA model. And so since we've been using x of t all semester for that already, how about we just use it now here for the error term? So to understand then this dependence that we have with the error terms, the procedure that's followed is that you first estimate one of these regression models, assuming independence. So a record-old regression model. Then do an ACF and a PACF of the residuals that we get, because these residuals essentially estimate what we normally think of as epsilons. Here it's going to be x of t. And you use then the ACF and PCF to help guide you for what kind of dependence actually exists amongst the error terms. So how do we estimate these models? There's a few different ways to estimate them in R. We are going to focus on what I think is the simplest way for our course, given what we've done already, and that is to use the ARMA function. And I have to admit it's not necessarily as, let's say, standard of how one would estimate one of these models as you would see, let's say, for example, with the LM function or the GLM function, where you have a formula equal response, tilde, explanatory variables. It's not that easy, but I still think it's the best route for our course. And so with the ARMA function, we use this xreg argument that we first saw with the drift term. And then to do forecasts of the future, we can use the predict function. We have a new xreg argument that's used to indicate the corresponding explanatory variables in the future. And of course, then that is an issue then with using these kinds of models. You need to know what these future values are for your, in this case, our z's, in order to forecast the future. And, maybe in some situations, it seems logical about what to put in for those future values. Okay, so that's a brief review of the corresponding material here for today. Were there any questions about it? Okay, let's talk about project number 4 then. So grades were good again. So you had to find basically the best model for these 2 data sets that we've seen earlier in the semester. Let's first talk about the earthquake data, and then we're going to spend more time on the Shiny app data. So with earthquake data, I had you examine 3 different models, or at least 2 of them were suggested based upon what we had seen previously in another project. But I thought, okay, let's just throw another model out there just so that you can see what happens when you have something. Maybe it's not necessarily as obvious to, or I guess you could say not as obvious to look at. And there was one thing that came up that I wanted to mention. And so with this ARMA 001 model, a number of you indicated that there was a small value at lag 9 for the junk box Pierce test, or at the very least it was, let's say, marginally significant. So what we're talking about then is what we see right here. Okay. Now, of course, why did you say that? Well, we can see how things are starting to dip down, and we're getting closer to this line, this dashed line that's drawn at 0.05. It's kind of close, so I'm going to say it's marginally significant. You got to be careful, though, with understanding the scale that we're using here. And if I were to, well, first of all, let's just erase this. If I could somehow, I'm not going to do a good job here, draw a straight line across this plot, we're going to see that that dot, or that open circle, is much closer to 0.2 than it is to 0.05. And, you know, if you take that into account, you're going to think, well, you know, would you ever say something's marginally significant if you had a p-value of 0.18 or 0.19? Generally not. But yet some of you did do that, essentially, in the project. So it comes down to, how about we actually find then what that actual p-value is? How can we do that? We have this displayed. I imagine that none of you probably actually found the numerical p-values. But is there a particular function that we could use to calculate the actual p-value? Well, I'm asking you because I know there is. Let's talk about how we can find it, because this will also help us understand how R does its calculations in general. That, well, it's definitely useful in this particular class for this particular situation. But the steps that I'm going to go through here now are steps that you should think about for other applications outside of this class when you need to know more about what R is actually doing. Okay, so first of all, there is an actual function called box.test that will actually calculate the p-value for you. I briefly mentioned that in the notes. I didn't actually ever use it directly in the notes. Instead, what we're essentially using to calculate these plots is my function, this examine.mod, which all of you use. And if you look at the very bottom, you know, what information is given to you that you can extract from if you were to save the results from examine.mod? Well, we only have the z test statistic for testing the phi and the theta parameters, for example, and then the corresponding p-values, not the p-values from the Jung-Box-Pierce tests. And that's where now, and again, you can apply this in other settings, you can now look inside this function to see, well, where are the actual calculations that were used to generate this plot of the p-values? Where did it come about? Now, what we did see in the model building section of the notes is that the tsdiag function is basically what constructs the first of the two sets of plots that are produced from examine.mod. And so you might be thinking, okay, I bet I could somehow get the p-values out of tsdiag so that I could actually look at the numerical values. So let's look at that a little bit further. Okay, so suppose I've estimated my model. It's in mod.fit001. This is actually what I use in the project itself. And I can use tsdiag to basically reproduce. Oh, you don't need to see that. I use tsdiag to produce this particular plot. Now, we know that when we run actual tsdiag itself, I don't actually have any information that comes back to my screen. So I don't have those p-values, the numerical values. So you might be thinking, well, wait a second, how about if I just save the results from tsdiag and print them off? Maybe I get some useful information. Oh, I don't. Okay. So then that will lead you to, let's say, explore further what this function is doing. And so if I want to actually see what's inside the function in terms of the code, what do I need to do? I anticipate that this is an easy question. I hope it's an easy question and that you just don't want to speak up because it's an easy question. How can I see what's the code inside a TS diag? Yeah. Okay. Now we have this. So what does that mean for us? What's special about TS diag now that we see? Because we really don't have much information. It's a method function. Yeah. And so if I want to see then the code for the actual calculation, I need to know the actual method function that's being run here. So what do you think I should do then? And we can review how method functions, or how so TS diag itself is actually a generic function. I should say that we're looking for the method function that's actually being executed here. And again, R is what's referred to as an object-oriented language. So that means depending upon the object, let's say like the main object that you're passing into this generic function, it's going to look at what the class is for that function and then extract that information and then try to find a corresponding method function that matches that class. So what would I need to know, or what would I need to do to figure out what method function I'm actually looking for? Key is right here. What would I need to do? So this is what I use to get my, what? Yeah. So I'm passing in this object that comes about from the ARMA function. So that means I need to look at the class of mod.fit 001. It's ARMA. Okay. And so if I wanted to, I could say methods class equal ARMA. Now I have a listing of all the corresponding generic functions that can be run with something that has the ARMA class. Notice TS diag is listed there. So that means there exists a TS diag function TS diag dot ARMA. It does actually exist, even though it says object not found, and I did not make a spelling error. How can I actually get that function? Get is a keyword. Get anywhere. Yeah, get anywhere. And there's the function. So let's look inside the function itself. How is it doing its calculations? And you can look at this for a while. The key thing is this right here. Actually, what I often like to do is this. I'm going to copy and paste this into a new editor window because now I have things nicely highlighted corresponding to what the corresponding aspects of the code does. And the key is this right here. So it uses a for loop. And you could go through this in more detail. I'm just going to explain it to you so that it takes less time. for I in 1 to the number of lags. Here's a little question for you. What does 1L mean? This is a tough one. This also deals with older times ago when we had to worry a lot more about how much memory a computer had and stuff like that. The L corresponds to an integer, meaning make sure that you treat 1 as an integer rather than 1.00000, because it's going to take up less space. Okay, so whenever you see an L next to a number, don't worry about that. It's just more older time code that people use. So 1 to the number of lags that are specified. I'm going to calculate a p-value, put it in the ith component of a vector that has the length of the number of lags. What I'm going to do is calculate that box.test, or use that box.test function. RS actually corresponds to the actual residuals that have been pulled out of the model fit object that you got from ARMA. The I corresponds to the number of lags. Now, it would have been much better coding if the authors would have actually put the argument name in front of RS, the argument name in front of I. Unfortunately, maybe they were a little bit lazy and they didn't do that. There's different types of tests that you can do with box.test. This is actually Jung box pierce, and then immediately extract that p-value. So this now tells me how those p-values are calculated. So now that I see this, I can take this out. I can put mod.fit mod.fit 001 $ residuals. I can put, I want lag equal 9. Unfortunately, off the top of my head, I don't remember what the actual argument name is. And now I can execute this. And there we see my p-value, 0.1685. That is not marginally significant. No one ever would say that's marginally no one ever would say that's marginally significant. So that's how I would get that p-value. Any questions about this? Well, like I said, I hope that provides a little bit of help, because I remember when I was in grad school, it was my second year, second semester of the master's program. Then I would go on for the PhD, same school. And it wasn't until then that we weren't really using R. R didn't exist then. S+ did. I had used it some, but not much. I was primarily a SAS person. And it wasn't until this point in my graduate career where I felt as though SAS was my friend rather than my enemy to try to get stuff done. It takes time to learn the inner workings of these software packages so that you can use it to learn rather than simply to calculate stuff. And so I tell you that short story because I hope for all of you, R will become your friend if it already isn't. It just takes some time. Let's talk about this Shiny app data. As I say here, this might be the most difficulty with a time series data set that I've ever encountered. And I want to say that here because I don't want you to think that all of the little twists and turns, especially those that we're going to be talking about shortly here, I don't want you to think that that is common. When I assign a particular data set for students to use in this class or another class, I do want a little twist and turn so you get experience with stuff. But there are a number of different issues that are with this particular data. There's too many of them, and there's some that you're just not going to typically encounter. So don't think that this is a typical data set. Some of these twists and turns I didn't really think about or discover until you guys started working on it. I suppose if I had to do it over again, I'd probably give you that UNL enrollment data set to have you work on for this project instead, because that was nice. And it worked out rather well. And why did this all happen? I think in a non-statistical reason is that there was a lot of things that were changing during the pandemic, and I think this is what brought this on. And while I really thought this, the Shiny app is really cool, and that it was beneficial to many people. I really wanted to do something more with the data that I had collected with it, but perhaps it wasn't a good choice in the end, because these twists and turns are such that it will be difficult for anybody to try to account for them in any kind of model. So the first one, and this is one I knew beforehand, and one thing that made me want to assign the data set is that there was a normality issue. Now, some of you didn't actually encounter the normality issue because you decided to make a transformation early on in step 1 of the model building process due to stationarity issues. And so if you didn't encounter normality because of that, that's fine. You decided to make a transformation because of non-stationarity and the variance. It was somewhat debatable. Yes, there were mainly short time periods where the variance was significantly less than other time points. I don't know. I kind of went back and forth if it would be really useful to make a change for that reason at the beginning of the process rather than go through the model building process some and see if you still have those issues. And I chose the latter. Now, hopefully you've taken a look at my answer key, especially if you made the transformation immediately. So let's say we don't make a transformation, we start estimating models, and we get a plot like this. Take a look at that QQ plot. Now, we've talked about it a number of times where, you can't be too picky with these QQ plots. But when I look at this plot, I see lots of observations that are really going off. And so that's what made me worry. And so this would then tell me, okay, let's try some transformations. Let's see what happens. And it just so happens that square root transformation tends to work out well. By far, the transformation that works typically the best for data sets in general is the log transformation. In this particular case, it didn't. The square root one tended to work well. One thing that I was concerned about when I was grading the projects, if you were taking care of the normality issue or possibly the non-stationarity and the variance issue, one thing that I was kind of disappointed that for some student projects is that students went immediately to the square root transformation without telling me, oh, I also looked at some other ones. And it got me thinking, maybe I'm wrong, but it did get me thinking, oh, I heard so-and-so's group use a square root transformation, so therefore, hey, let's try that one too. I didn't take off points for that, but make sure in practice though, you are actually exploring other possibilities. You're not immediately going towards, in this case, the square root transformation. So this occurrence, with the square root transformation, the normality is what made me think, okay, this is going to be a good learning tool. Then we start getting into issues. other issues. Because we have lower bounds of our confidence intervals that end up being negative, and of course, we have ones that are negative with the transformed data. Then when we transform it back to the original data scale, which you have to do because after all, that's why we're doing this. We want to predict these number of visits, not the square root of the number of visits. You got to transform it back. So now that negative number for that lower bound now becomes positive. And the weird thing that happens is that the actual forecasted value, so the predicted value in the future, now is less than the lower bound of the confidence interval. That happens with this kind of a transformation. It's interesting that it does, but that's what happens. And so, what can you do in that situation? For a few groups that mentioned this to me, I said, okay, well, one thing is that how about you just take the lower bound to be 0? That would be one possibility. Another one, the more that I think about it, another possibility that would be better is to use one-sided confidence intervals instead, where you have an upper limit, you do not have a lower limit, but you do know because of the nature of this data that lower limit has to be 0. And so now we do have 97.5% confidence intervals that we can use, or confidence interval limit. Or I guess you still call it a confidence interval, excuse me. And so those are two options of what you could do. Now, something that I didn't notice and was brought up by one group, how about a drift term here? We are taking differences. And at least Shumway and Stouffer, even though any other time series book that I've seen doesn't really mention this, or rarely addresses it, we could do a drift term here because we have that differencing. And guess what? When one does that, one gets an AIC that's actually lower than at least the final model that I chose. And I think pretty much everyone else chose the same model that I did. So at least with respect to the AIC criteria, the model with the drift term is better. And you could even do a hypothesis test for that drift term. And guess what? You do have low p-value. So, this got me thinking, I guess the next time I teach this class, for that model building section, I should put in a little bit in there. If you're doing differencing, take a look at that drift term too. I've mentioned to you before that this is only the second time I've taught drift terms. And that's why, unfortunately, I think why I left that out. Now, another issue with this that came up. And I posted something to the discussion board about this. And that is, if we take a look at the original ACF, look what we got here. We don't have extremely large autocorrelations. We don't have extremely low autocorrelations, but instead we have moderately large ones that are persisting across the lags. Of course, this kind of follows what you would expect for an RFEMA model. I think I mentioned in my discussion board post that when I put together this project originally in January, typically the way I do it is I'll take a look at my notes, do the project, in case I need to make any changes to my notes, then look at my next set of notes, do the corresponding project about it. And of course, then I got up to model building. I made this project. I actually did take a break from continuing with getting prepared for this course. And then I got back to it. And of course, then RFEMA was next. And it never occurred to me to think about, well, maybe I should go back and see this and think about this some more. So now, can you fit an ARFEMA model that has a seasonal component to it? Well, yeah, of course you can. Can you do it in R? Well, there is a function in R, not the function that we looked at, but there is the ARFEMA package that has the ARFEMA function. I mentioned this at the end of my notes for the section. And you're not responsible for you using that function, that package. Just the fracdiff one's fine. If you look at the help for ARFEMA, it says it will fit these models. I've tried to fit these models with this function to prepare for our class here today. I cannot get it to work. Maybe I'm just doing something wrong, but I can't get it to work. I hope that I'm just doing something simply wrong. Because you would expect that if someone's going to put this code in their package, in their function, that of course they've tested it and they've got it to work. Hopefully this is not an example of user beware when you use somebody else's package. If you remember in the notes, I said, why didn't I use this package versus the fracdiff package? I used the fracdiff package because I recognize the author's names. I know that they were ones who were developing this stuff. I had never heard of these people that were using who developed the ARFEMA package. And I use that often as a criteria when I'm given the choice between packages that are supposed to do the same thing. I use that as a criteria to make a decision about which package to use. Because a lot of R is you got to trust those people who are developing this. And I will tell you, not everyone who develops R packages is as how shall I say, they are not as close to attention to detail as you would like. I know, for example, for my analysis of categorical data with R book that I wrote, many times I have to go through into the details of these packages and the functions to make sure things are right. I have found numerous times where things were wrong. And so this is an example, perhaps this is an example of a user beware issue, and it doesn't work. Try it on your own and see if you can get it to work. If you do, let me know. Again, maybe I did something wrong. Another issue with this data set. No one mentioned this. Phi hat 1 was 0.9845. I noticed this before when I was doing this project beforehand, but I decided to just see what happens, see if anybody would notice it. Why is that important? Well, when we write out, let's say if we just write out an AR1 model, if this phi 1, not phi hat 1, but if phi 1 is 1, that means you have differencing. And so whenever I estimate one of these models that has some kind of autoregressive part to it, I always look at that. And if that's getting close to 1, I start worrying that perhaps I need differencing instead of an AR term. And one thing that I do is I look at what's the standard error associated with this parameter. And if we look at that, now, we're going a little bit longer than I want to, so trust me, it's only one standard error from 1. We think of plus or minus 2 as a general range, you could say, for like a confidence interval. So that confidence interval essentially would contain 1. And so that greatly concerns me, because then that says I don't have stationarity. I still have more to take care of, even after the seasonal differences. But after you do the seasonal differencing, if you look at the ACF, if you look at a plot of the seasonal differences, there's really no evidence saying that indeed you have non-stationarity. So for that reason, I said, when I was constructing this project, I'm just going to move on because I don't like it's close, but I don't see any other evidence of a problem. So I'm going to move on in the model building process. Another thing that a number of you brought up, which is good, is that you notice that seasonal theta hat 1 was estimated at least to 4 digits, 4 significant digits, or 5, 1.0000. And, whenever we see, again, something like that on the AR side of the model, we would get, well, hopefully you would get worried. On the MA side of the model, it's not as much of a concern. It is a concern, but not as much. First of all, though, I did not see this. So if you actually put in then the parameter estimate, you have 1 minus b to the 7th power on the right side of the model. Of course, on the left side of the model, when you're doing seasonal differencing, you have 1 minus b to the 7th power. Oh, they cross out. That's strange. We don't want that to happen. And when that was brought to my, when that fact was brought to my attention, I was surprised. And I've looked inside the code for ARMA, and there are checks in there for some of these issues. And my best guess then is that phi hat 1 is not exactly equal to 1. If you actually look at, do mod.fit $conf, you will actually see that indeed it is not equal to 1. So it doesn't quite cancel out. And so that's why I believe why ARMA is letting this go. Now, though, we also have the issue about, we need the roots outside the unit circle of these polynomials, both on the AR side and the MA side. The AR side corresponds to stationarity issues. Causality issues. The MA side corresponds to invertibility issues. What is invertibility? Well, it means then, just as a review, it means that I can rewrite my model as an infinite order autoregressive model, and I have essentially a unique representation for it. There was a nice example in the notes that shows if you didn't have invertibility, you basically could have 2 different values of theta to represent essentially the same model. But in the end, you do have a model. It's not as big of an issue as causality, where you don't want a model that's future dependent. And so I decided to look further into the invertibility issue some more. And here's an interesting quote then from Shumway and Stouffer's book. For convenience, by mimicking the criteria for causality of AR models, we will choose the model with an infinite AR representation. In other words, we choose the model that is invertible. So that's why I say it's not as big of an issue as causality. So that, again, we do have roots actually outside the unit circle. It's close. And so anyway, so that gives you a little bit of more discussion about that aspect. 2 more things I want to talk about regarding that came about with this project before we get to the test review. First of all, there was a group that decided to compare models that were models for x of t and then also for the square root of x of t. Compare them based upon the AIC. I bring this issue up, not to pick on that group, but I bring this issue up because I want to make sure that all of you understand, don't do that. The reason is, think about what's inside that likelihood function. You have, you can think of it in any, even, situations outside this class, like the first time that you ever saw a likelihood function. And let's say you have two choices, working with x or the square root of x. Maybe a normal distribution for it. That likelihood function is going to change simply because, the likelihood function is going to be different simply because you have now two different scales of data. You have the x data, you have the square root of x data. And so if the likelihood function will be different just simply because of that, you cannot compare those two likelihood functions. Therefore, you cannot compare the AIC for those cases. That's why you will want to avoid that kind of a situation. This also brings up something else that I've seen sometimes students do when I've taught time series. I thought it was my notes, and I looked through my notes. I could not find it. If after I go through this, you say, yes, it is. If you say, yes, I do remember that it's in your notes such and such place, let me know. And the comment that I want to make is as follows. You cannot compare, based upon the AIC, models that have x of t and also models where you have, let's say, first differences of x of t. Why? The reason being is because essentially, if you take first differences, with my original data, let's say I have n observations. Now, if I think of my first differences as being a new data set for, let's say, y sub t, how many observations do I have now? N minus 1. Okay. Think about how likelihood functions formed. You are essentially summing up stuff, well, a log likelihood function. You're summing up stuff over n observations if you are working with x of t, versus y sub t, you are now summing up observations over, you are summing up over n minus 1 observations. So a likelihood function for y sub t could simply be less than the likelihood function for x of t, simply because there's less observations that you're summing over. And if that's the case, again, think about how the AIC is constructed. You have a likelihood function plus a penalty. You cannot compare these two situations for x of t and y sub t simply because there will be less observations for y sub t than there will be for x of t. This might have a smaller AIC than this simply because of the fewer observations. So only compare AICs based upon just all the x of t's, models that you have for x of t's, or after you've done the differencing. Just compare those models with the differencing only. Does that sound familiar at all that I've brought this up anywhere before? Okay, well, good. I'm glad I did. This issue did not occur in this class with our modeling here, but I've seen this occur other times, and I had thought that I had included it, but obviously I did not. I'm sorry. Okay, so those are some good interesting things that came about with this project. Everyone did well on it, though. Any questions about the project? Okay, well, let's talk about the test then. So, same format as last time. You'll be using the computers here in this classroom. Make sure, when you get to class on Thursday, you immediately log on. I know some people have had sometimes difficulty with the logging on procedure. It takes a little bit of time. So make sure you're ready to go by 9 a.m. It's a closed book, closed note, closed video test. Can't talk to other classmates or anybody else during the test, of course. But you do have access to my R programs. You have access to my my PDF that contains important equations if by chance you need that. Please remember, we will start at 9 a.m., not 9:30. You can go till 10:45. If you absolutely need a little bit more time, that's fine. I don't want to go past 11. When you get done with the test, please email it to me. Do not leave the classroom until you receive a confirmation that I received it. Of course, computer issues can happen during the tests. We have lots of computers here, so you can always use another computer in this classroom if you start having computer issues. If you want to, you can also bring a laptop as let's say, an ultimate backup to complete this test. Please remember that you to study enough for this test. Since you do have access to my programs, some students can sometimes get overly reliant on those programs if it takes you 15 minutes to try to go through all my programs to figure out how to estimate an ARMA model, that tells me you haven't studied enough. You've used now ARMA enough that you could probably type out the code for ARMA without even looking at one of my past programs. If you don't feel comfortable doing that yet, make sure you get to that level of comfortableness. So the structure of the test is the same as last time too. Typical problem types are, okay, here's a data set. I want you to do some stuff with it, like estimate a model, then do some interpretation of the model. Those are the typical kinds of questions that you see on my tests. You may have to derive a quantity. I would say, actually, you will need to derive a quantity. I'll mention that shortly coming up. There is, for the last problem on the tests, there is a short answer problem set. In this particular test, I have 4 short answer questions where they're not interconnected in any way. Please make sure to always show your work. If the problem asks, compute the actual forecasted value for time 101, if you only give me that numerical value, you're not going to get full credit. I need to see how you got that. Obviously the quickest way is to use the predict function. Give me the corresponding code that you used. That shows me that you understand what you're doing. Also, when you have to do derivation, don't just immediately state, okay, this is what I'm looking for, and then voila, I got it in my second line, I have derived it. Show me the process that you used to do the derivation. When you're doing hypothesis tests, state the hypothesis so I know what you're testing. And all these extra things that you need to put with your answer is to help you so that I can give you partial credit when things go wrong. Again, there's going to be times where you're going to need to work with equations. I encourage you to use the equation editor in Word, but it is okay with me that you use some kind of text-based equivalent. So if you need to say, for example, phi1, it's okay to say something like phi_1, or just phi1 itself, or in terms of phi_1. You do need to use the same notation as we have in our course. Are there any questions about the test format? Okay, let's do a little bit of a review then. So the material on the tests starts with subsection 10 of section 3, which is forecasting. So right after we got done with model fitting. Now, of course, you do have to have some understanding of the stuff that we did before that, like what is an ARMA model. But I won't, let's say, ask you direct questions on that previous stuff. So we go from forecasting up to the ARFEMA stuff. So none of this regression model with ARMA errors that you needed to examine for today. So with respect to forecasting then, what are we doing? Well, we observe information up to time n, and we want to go m different time periods into the future to understand what that numerical value would be for whatever we're measuring. And so we have kind of an intuitive way of thinking about it. How about we look at, well, what would I expect this unknown value to be given information up until time n? So it's a conditional expectation. We have this kind of a weird symbolic way to denote this expected value, where we put a tilde on top of the x, n in the superscript to mean we have information up until time n. So if n was actually 100, you would see a 100 up there. And then in the subscript, just like how we have here, we have, well, what time point are you actually interested in? Now, we know that when we estimate this quantity is not going to be perfect. And so we would like to understand what's the variance of how far we're off. And so this is then the variance of the forecast error. Make sure with forecasts and this variance, you can derive it. On the tests, there will be a time where you need to derive a forecast. You will need to derive a variance of the forecast error. Guaranteed. Now, if I asked you to actually compute one of these quantities, I could say, okay, take what you derived and plug in the actual, let's say, estimates of the parameters. I could ask you that. Or I could say, hey, just go find these values the easiest way possible, which would be, for, of course, use the predict function. With this, then, you can find confidence intervals. You can also do some nice plots of what these forecasts would look like. Then we got into this short section on the drift term. Make sure you understand, well, why would this be important to us? It kind of goes back to how it was originally introduced with respect to these random walk models. How do we estimate it? Well, we use the ARMA function, and this is then when we first saw the xreg argument. How do we forecast future values? Well, then that's when the predict function comes in to play. We use the new xreg argument for the forecasts. Then we got into the model building process. So that took a lot of the stuff that we've seen previously, put it all together. We added some additional stuff, and we're trying to find the best model possible for our data. There are 6 steps. We have this examine.mod function that I wrote to help simplify the process for you. Make sure you're very familiar with how to use it. A key aspect to evaluating these models is to look at the residuals. In other words, these estimates for the W's. We assume that these W's have a normal distribution and they're all independent. So we have a variety of different ways that we can investigate these estimates of these W's to check to see if that actually occurs or is, let's say, reasonably satisfied. Now, on the tests, I'm not going to ask you, hey, here's my second shiny app data set that I want you to now go ahead and find the best model here in the next hour. I'm not going to ask you to do that. But what I could ask you is this. With this data, suppose we've gotten up to step 2 of the model building process. What's the next step? I want you to actually implement just that next step. Or what I might do is, okay, say, come up with all these diagnostic plots in step 4. Tell me what they say. Tell me, should changes be made to the model? If so, what changes? Don't actually implement them, because that's going to take too long. Just tell me what should be done. And so what I'm trying to say is that here, on the test, I might ask you to perform 1 or 2 steps. Not all 6. In the past, sometimes too, what I've done is say, okay, here, I've actually done all these plots for you. I want you to go step by step, go through each individual plot and indicate what they are telling you. Now, also in this section inside our Tuesday classes, we also did this AIC Monte Carlo simulation investigation. I might ask you some questions regarding that as well to make sure that you understood what we were doing. So after model building, we got to now stream of models. So now we can take into account seasonal aspects to our data, which frequently occur in time series, weekly data, monthly data, and so on. And why do we want to do that? Well, if we're observing, let's say, data that's collected monthly, what happens in January of 2024, that might be closely related to what happened in January 2023. We want to take that into account. And so this is what our full-blown model looks like in terms of having AR and MA operators. How do we then interpret an ACF and PACF for these potential models? With respect to the seasonal aspect, we're looking at, if we have weekly data, well, we're looking at S equals 7. Or let's say lag equals 7, lag equals 14, lag equals 21 on these plots to come up with some kind of interpretation. You could actually derive an autocovariance or autocorrelation function associated with one of these models as well. Of course, we're going to be interested in forecasting. How do we estimate these models? Well, we use ARMA again, but now we have this additional argument called seasonal. Make sure you're comfortable with doing that. How would we proceed with model building in this situation too? That's all important. Excuse me. Then we got to our FEMA models. When do we use them? Well, long memory, where these autocorrelations just don't seem to die out. But they're not extremely, extremely high as you would have when we need differencing for stationarity purposes. So this is what our model looks like. And because of this D is going to be between 0 and 0.5, we cannot necessarily write this model so that we have, let's say, like an alpha on the right side of it. And for that reason, and because we might have a non-zero mean, we have this x at t minus mu that is right in there. Now, with these kinds of models, make sure you're comfortable with ACFs and PACFs. Again, use that frac diff function to help with estimating the model, doing the forecasting, and how would we actually go about doing model building in these situations with this kind of a model. Okay, so I've already addressed this particular part right here, well, where you will actually have a derivation regarding the forecasts and also the variance of the forecast error. These are just important things. That's why I often like to put these on tests. Okay, so that's all I have to say specifically about the tests. Are there questions that you have?
Was there a reason why the fractional powers of E is between 0 and 0.5 and not more than 0.5?
Off the top of my head, I don't remember what the reason is. I mean, we are doing some Taylor series expansion. I have a feeling it has something to do with that you're going to have problems with things not working out with the expansion. Right now, that's the best answer I can give you. I know people at one point would actually look at 0 to negative 0.5, but that's typically not done anymore. But at least right now, that's the best answer I can give you about that. Sorry. Are there other questions? So let me just emphasize that I want all of you to do well in this test. I want all of you to get a 100%. Of course, that shows that you've learned the material, but also makes it easier for me to grade too. Okay, so I do want you to all do very, very well in this test. So if between now and the test you do have questions that come up, post them to the discussion board. Because I bet if you have that question, probably somebody else does too. And that way everyone can learn from hearing my response. So if there's no other questions at this time, let's just end with, well, what's next in our course? So today, if you do have more questions, you just want to talk to me individually, go ahead. I will answer those for you. You do have a quiz that's due at 8 p.m. on Canvas, so please don't forget that. On Thursday, I will be here at 8:30 for my normal office hours, but we will take then the test starting at 9 a.m. Then next Tuesday, my usual office hours, class at 9:30. 2 subsections, a little bit less than normal because of the tests. The first subsection deals with multiple time series. So instead of just observing, let's say, x1, x2, down to xn, suppose we also had y1 down to yn, or z1 through zn, and so on. You could have that. You saw that a little bit with that LA pollution data example when we had a regression model with ARMA errors. To some respect, it's kind of like that. But suppose we wanted to maybe address some of these issues more so in the same kind of ARMA kind of format that we've been using just for x of t. You can do that. So for example, there are what are called vector autoregressive models, where you could imagine, let's say, now suppose we observe this information, a vector of information over time. And so what this first subsection does, it says, okay, let's start now looking at measures of dependence, similar to what we did before we got into ARMA models. Suppose we look at these measures of dependence, such as like the equivalent of an autocovariance function, when we observe these kind of data. Unfortunately, we won't get to that vector autoregressive model. That's like the next thing I want to add to this course, and we won't get to it. But at the very least, this is going to help set you up if you want to do some further reading in later parts of the Shumway and Stouffer book. It will help you get going on some of that stuff if you want to. So that's the first. You also have concepts of stationarity as well with this. Then the last main topic then that we're going to discuss in this course deals with what's called autoregressive conditionally heteroscedastic models, or more simply put, arch models. This is a topic that doesn't happen, I think, in most one-semester time series courses. I started adding this probably about 10 years ago when I was teaching this, because I think it's an important topic. It's something that you do see pop up in time series a lot. And in particular, one way to think about it is that we've seen cases where we have non-stationarity in the variance. We could do a simple transformation that hopefully helps it. Here's a different way. These arch models basically allow you to construct a model for the variance itself that's time dependent. And you can combine that with also models for just regular old x of t that we've seen before. So this allows you to have variance that's time dependent. One of the cool things about this model, these models, is that this model was the individual who created these models was awarded the Nobel Prize for Economics about 20 years ago for its development. And so this is one of the few places in a statistics course where you actually encounter something like that. And so that's really interesting. In addition to arch models, eventually we'll get into what are called GARCH models, and you can imagine the G is for generalize. These GARCH models are widely used in finance because very often this is where this non-stationarity occurs. We're without getting into all the details, we're trying to model the variance. The variance has a very special meaning when it comes to investments. Variability in terms of, let's say, how much your stock is going to make today versus tomorrow or the next day and so on. That, if you have a lot of variability, that means you have a lot of risk. And people in finance are very interested in understanding risk. And so that's why these models are widely used in that kind of a situation. So for those of you who are following along in the book, those are the corresponding sections. So you can see we're getting into section, well, I guess we already did that. I will tell you, though, the book doesn't go into as much detail about arch and GARCH models that I think is necessary, so my notes are actually much more than what the book does. So we also will discuss test number 2 next Tuesday, and there will be still a quiz that's due. Looking further ahead, our final exam is Thursday, May 16th at 10 a.m. Do note that I accidentally have I did not put the time right in our last class. It's always been correct on the schedule webpage, but I noticed when I was going over all this after class, I had put the wrong time. Of course, I want you to be here on the right time. Any last questions? Okay, then that's all for today.